שוב בוקר טוב לכולם וברוכים הבאים לוובינר שלנו, וכמו שאתם כבר יודעים שהוובינר היום הוא בנושא של 5 צירים, הטכנולוגיה שבתוך ה5 צירים, על המסלולים החזקים שיש לנו שם, ורק שתראו היום ה5 צירים של SolidCAM הוא נחשב כ5 צירים סימולטני הכי חזק בעולם, אבל לא רק שהכי חזק בעולם, אבל גם כן הכי קל להשתמש בעולם. עכשיו, הוובינר היום, אנחנו מבינים אותו על ידי בחור שקוראים לו עמוד, הוא בעצם המומחה שלנו, ובעצם המומחה הכי טוב שיש היום בכל השוק, על הנושא של 5 צירים סימולטני, גם כן כרגיל בסוף הוובינר יהיה לכם זמן לשאול שאלות. אם יש לכם שאלות בנושא, על כל נושא של הוובינר, אפשר לשאול אותם על ידי זה שאתם לוחצים על הכפתור raise hand, כותבים את השאלה שלכם באזור של השאלות. כמובן שאתם מסיימים לכתוב את השאלה, לא לשכוח ללחוץ על הכפתור send, ככה שאנחנו נראה את השאלה בסוף. אז וובינר בעצמו הוא יעבור את זה באנגלית, והוא ידבר רק ככה שיהיה מאוד קל להבין אותו, וזהו, עכשיו אני אעביר את הוובינר לעמוד. עמוד, good morning or good afternoon, and I will make you the presenter now, and you can start your webinar. And everyone, I'm sure, will enjoy the webinar, as I know I always enjoy webinars as it's being going. So I will make you the presenter, and you could now start the webinar.
All right. Boker Tov, good morning everyone in Israel. My name is Amod Onkar, and I'll be your host today for showing you some very nice stuff inside 5-axis simultaneous in SolidCAM 2013. As you know, that SolidCAM has been making strides and progresses into the 5-axis area of milling. So there are very nice features that have been developed and ported on SolidCAM 2013 in the area of simultaneous 5-axis, and some of them have been very interesting because they have been on the wish list of many of the users from pretty long time. What I've done today is, because it's a long list of features and new stuff that has been introduced inside SolidCAM 2013 in 5-axis, we have broken down the whole webinar into 2 halves. The first half you're going to see today, and the second half you're going to see in the later part of next week on the same day, basically on a Wednesday. So I've just divided into 2 halves to get a better feeling of the product, because there are a lot of changes, and there are a lot of new stuff that has been added, which takes some time for us to go through it. It's a long list. And what I've done here is I've taken that entire list and I've put it across 3 major areas where I've classified the features according to their application industry. For example, we have some very new stuff called as multi-blade machining. So we have the multi-blade machining, which I have put it as an application meant for aerospace, which it is. And then we have very nice stuff that we have created inside, using the regular 5-axis to machine turbine blades, both for steam turbine as well as for gas turbine. And then we have the new swarfing function that can be used for machining frame parts for aerospace application. We also have got some nice new features for automotive trimming parts. For example, if you have vacuum form parts, you could do the trimming of this vacuum formed parts using the new function that we have inside SolidCAM 2013. We also have a very nice function to machine the engine ports cutting for automotive as well as aerospace engines. Using a regular 5-axis functionality, which is very powerful inside SolidCAM, we'll also show you how to cut molds of tires, which is another big application in automotive. Once we are done with the aerospace and automotive, then we have functions that we have put in die mold and styling. For example, machining fine features using simultaneous 5-axis in a mold. And then we have 3 to 5-axis conversion, which is very fast and very quick and very effective. You can convert an existing 3-axis HSM tool path. You could apply some automatic tilting mechanisms, and it could convert an existing 3-axis tool path into a full-blown 5-axis tool path without having to spend much time on the entire thing. And then I'll show you some features. This all will happen only next week for super finishing of molds, for multi-axis drilling in 5-axis when we have a model. How does SolidCAM identify the entire features available on the model and converts them into drilling program using the 5-axis engine. And not but the least, the STL machining, because this is also very crucial for people who do prototype machining. Since most of their prototypes are scanned prototypes, we will use the STL machining to cut the part in 5-axis in STL using the STL geometry. Right, let's jump now into the software, and I'm going to open up a nice part. This is a portion of one of my customers' part. So this is a live example, and let me open up swarfing. I have a portion of a big aeroframe structure, and what I would like to show you is how we do the swarfing of such parts in using the new swarfing function. I'm going to show you 2 ways of doing it. One is a pretty automatic way where it generates results very quickly, and in the similar kind of a pocket where we are not able to generate it automatically, how we can further tune up the entire tool path using some new tilting mechanisms available in swarfing to generate a very effective tool path. All right, like you can see, it's just a portion of a frame part, and we are going to swarf these faces, the ones that I'm marking at the moment. Now these faces have 2 different angles. For example, a face out here, the one that I marked now, has a positive angle. It has got a big positive angle. So how do I analyze it? So if I go to measure and analyze the angle between the bottom surface and the face out here, it is 104 degrees, which is like about 14 degrees to the vertical. So it has a positive angle of 14 degrees. And if I analyze this angle out here, it has got an angle of 77 degrees, which means it has got a negative angle of almost 13 degrees. And then we have a patch out here where there's a blending that's happening between minus 13 to plus 14. It's almost a difference of 27 degrees. You could also run in the part analysis itself. If I edit this part and if I go to draft angle analysis and select the face below here, it gives me a very quick analysis of how my draft looks like. The green is all positive draft, the red is all negative draft. So we have this area like I explained below. There is the area out here, which is basically a blend from negative to positive. So you have got a positive 14.76 and you have got a negative of about 13 degrees out here. All right. So, and the other 2 faces, by the way, are absolutely straight. They don't have any angle. So you have got again another blending happening from the positive 14.76 to a straight 0 degrees. So it's a very interesting scenario where we have negative and positive, high negative and high positive coming into place. All right. Going to be out of the draft angle analysis and out of also the part edit mode. So we have under operations, or you could also right click on the setup, add milling operation, and we have this new swarfing function. This function was already there before in SolidCAM, but it has been greatly improved upon to generate much more consistent results on any kind of geometry. So let me run the swarf. Like the new functions that have been developed inside SolidCAM 2013, the new functions now take into account minimum input from the user. Because if you look at our regular 5-axis function, one needs to input a lot of things, including the geometries, the tilting geometries, check surfaces, angles, tilt angles, lead angle, the step order. A lot of things have to be input before you get to generate the program. But with a new engine of swarfing, you really don't have to worry with the inputs, because the inputs are bare minimum in the newer functions of SolidCAM. So now if I go to the logical step of defining the geometry, you can see that first thing that we have is a strategy, which is automatic. I don't have to worry about it. But it doesn't mean that everything is going to be automatic and for every time you're going to get a result. We know that realistically, maybe we have a chance of about 0.1, 0.5% that we might not get a result with an automatic function. That is the reason we have given few more options. But we have seen that 99.9% of the times, the automatic comes up with a great result. You don't have to really touch any other strategies at all. But we still have come up with strategies in order for you to experiment which could be probably a better result. But for this part, for this webinar, I'm going to use the automatic function. And the next thing I need to define is the surfaces that need to be swarfed. Now, I'll click on New. I need to define on which surfaces I need to swarf, so I'm going to select those surfaces. These are the surfaces. All right, these are the surfaces that I just swarfed. I'm going to say, let me give a name to these. Swarf surfaces. All right, let's say OK. Since we also have fillets and the floor below, we need to define the surfaces as our floor surfaces, else the tool will not find that there are surfaces below, and it will try and cut through these surfaces. Now, in order for us to stop that tool exactly on those surfaces, I need to define the floor surfaces. The floor surfaces in this case are going to be 1, 2 fillets, the entire fillets along the periphery, and the bottom floor. Okay, there we have. We have selected these as our floor, so I'm going to give the name as floor surfaces. Okay. If I need to give an offset, I can provide an offset to the to the surfaces that I'm cutting using the swarfing function. And if I want to stop the tool much before the floor surfaces, I can define a floor offset. So I can define the swarf offset as well as the floor offset. Sorry. Let's pick a tool. I already have a 12 diameter ball nose. Okay. Levels. I want the plane height to be about 50 mm. That it's taken already from the coordinate system definition. I'll enter the safety distance as 5 and the exit safety distance as also 5. We can now distinguish between the entry safety distance and exit safety distance. This is one of the new features of 2013 of SolidCAM. If I go to the toolpath parameters, my cut tolerance is 10 microns. Start point is exact. I can specify where I want to start my toolpath or the machining side also is very important, because since we have picked the surface, it can have two different machining sides. It can have left or right, depending on how you have picked it. You could have inside or outside, depending on which side is the normal direction, or the system could do auto detect. It could run a normal analysis on the surfaces and detect which is the side to be cut. But we are going to help SolidCAM here, and I'm going to tell SolidCAM to cut from the inside. It's going to be one way and climb. If I go to the tool axis control, you can see there is no much buttons out here. Everything is the same. We don't need to specify many things in tool axis control, which is one of the crucial elements of 5-axis. But since this is a new product that has been integrated inside SolidCAM, a lot of things have been automated, and tool axis is one of that, one of those areas that has been automated. Link, of course, I would like to use a lead in and a lead out. I'm going to use a tangential lead in, and I'll use a 1 millimeter height. And the lead out also is the same, tangential with 1 millimeter, so that doesn't rub the bottom surface. All right. Once we have done that, we don't need to define anything. I don't need to touch this unless and until I'm very much sure that there has been a gouge. Otherwise, most of the times, the tool paths are gouge free. Right. We are not going to do any roughing, but we can also do roughing. I'm going to show you once we generate a tool path. Let me save and calculate this tool path. Okay. I already have the toolpath, and if I show you the wireframe version of the toolpath, pretty clean with the lead in and the lead out. A very clean toolpath. Let's run the host CAD itself with the tool, and I would like to show you some positions in the tool, how smartly SolidCAM does those positions. Now I can look. What it is doing is it is engaged itself. It's exactly rubbing, or it's exactly touching the side of the wall. But if I go to the side view on this side, you can see what's happening actually. Okay, let's go on this side. You can see what has happened. SolidCAM has tilted the tool, but this tilt is in the lag direction. There's a lag that's happening. Why is this lag happening? The lag is happening because if you note, when we did the draft angle analysis, we had a positive draft surface out here. Now this surface is actually influencing this lag. But if you note, this surface doesn't have any draft angle. But that doesn't matter because the lag is not changing anything on this draft surface, on this surface where there's no draft. So it's smartly doing that. You will notice when it comes to the end why it did this lag. Okay, let's move further one step, and you can see that the lag is changing now. The lag is changing and it's gradually becoming parallel. If I go to the side view again, it's going to gradually become parallel to the surface which does not have any draft. So it's now turned itself, and you can see that it's now parallel to this surface. If I look from this view, it's parallel to this surface. But if I change the view, if I go here and if I go into this side, you can see that it's already started changing its lag angle again. It's changing the lag. Why? Because it's now approaching a negative surface out here. So it's very smoothly changing over to the next angle without affecting the machining of the existing surface. Now you can see it's cutting this undercut, but if I again go to the side view, you will see that it has already started adjusting its lag in such a way that it is now ready for the next surface, which is a positive draft. But if you again look from this side, it's put that same angle as a tilt angle. It's put that same angle as a tilt angle. So it's doing two things now. It's changing the lag into tilt, and it's now adjusting to the next surface again by putting a lag angle. Very smart. What it does basically is it reduces those jerks on the machine and gives the machine to move or roll over much smoothly. Right? So let's go here, and you can see now from here there's going to be a slight adjustment because it needs to blend in from the negative to positive. So there was a small adjustment of angle, and it's going further. It's following the same angle, and as it comes and exits and comes towards the point, you can see that it was carrying that same angle of positive all over here. It did not change the angle because that would have again resulted in some surface variations in terms of finish. So it has kept the angle as close to the influencing surface as possible so as to avoid any variations in the surface finish on the surfaces that it is cutting. Very smart. So we have now the tool path. Now we could go into roughing, and we could put roughing slices. For example, we have got pattern, and then we could say by number of slices, I want 10 cuts in the tool axis direction. Okay, and I've got pattern layers. I can put multiple cuts in the actual direction of the cut. So I will say I want 3 with a layer distance of 5 mm each. Now, how do I want to pattern out the top point and the bottom point? I want to morph them between the upper edge and the lower edge. That means it needs to morph from this upper edge to the lower edge, which it will do automatically. So let's calculate it again now. Okay. It's already done the calculation. Let's run the simulation now. Let's quickly run the simulation without the tool, and I will show you how the toolpath looks like. You can see that it has got 3 layers, the pattern, and then it has also got axial cuts, so many axial cuts. So what it is going to do is it's going to start from outside, finish all the way below, and then it is going to the next one, finish all the way below, and then it's going to the next one. So if in areas where you have done 3-axis roughing and you know that there is a lot of material remaining, you could use this mechanism, this method to fix, to take multiple cuts actually as well as depth-wise to cut this part safely. All right, so what I'm now going to do is I'm going to do the same thing for this side. So let me add the swarf operation. In the geometry, I'll pick the surfaces that I need to cut. Okay, I've got some small surfaces out here. Okay, these are the surfaces. Done. I also have floor surfaces, so I'm going to define the floor surfaces also. It includes this floor and the fillets along the floor. Including the small patches. Okay, there's a small surface still remaining, and that's that one. Okay. So now I have got the drive surface as well as the floor surfaces done. I'm going to select OK. Let me pick the tool. Levels remains the same. I'm going to have 5mm entry and 5mm on exit. Toolpath parameters, I would like to cut it inside. One way. tool axis, it's going to be the default. Link, of course, we're going to use the lead in and lead out. I'm not going to change it. Gouge check, I don't need to do anything. And since I'm just going to do one slice, I don't need to bother about roughing. Let me save and calculate. And let's check how this toolpath looks like now. So if I run the simulation, the toolpath looks pretty much clean. But what is not clean, or what is problematic, is this area. If you can see that it's not a clean area for me here. I have let me open up the toolpath. Okay, you can see that it should have ideally moved around this fillet, but I see a very sharp corner out here. We have to now find why this is happening, and in a moment we'll find out why that is happening. Let's go out and let's run the HostCAD simulation. Okay, I'm going to right click, run the simulation with the tool on. Okay, and go step by step. Okay, fine. This looks okay. This also looks okay because it needs to go on those positive surface. This also looks okay. It's now going to roll over that fillet, and it's now adjusting itself to come to the front surface. That's also fine. But then you can see something else is strangely happening. What is that? Now, because this particular surface is straight, it should not ideally change this angle, which it is now doing. It's doing something very strange. Okay. And first of all, there was a blip. It changed the angle in a very short period. And let's see what happens. Now you can see that the tool is now trying to become almost horizontal, and we have no idea why it would perhaps do this. And it's doing a very strange movement out here. And then as it comes closer into the wall, it's adjusting. Now this is a very dangerous move. I mean, your entire machine, depending on the kinematics of the machine, if it's a head machine, could take a major turn in a very short distance, and this could be catastrophic for the machine. Let me go ahead and see, because I had highlighted to you one of the problems. Let's see what is happening there. Again, it's the same thing, and it's finished. Right, so we now know that there is some problem out in this area, and we really don't know what could be the problem. The solution inside swarfing is pretty simple. So let me edit, because I could not, since I put it on automatic, I could not control the tilting of the tool. I'm now going to position few edges of the model, and I'm going to ask SolidCAM swarfing to position itself parallel to those edges whenever it is close to those edges. So I'm going to go into the geometry, and I'm going to pick up some tilt lines. Okay, I'm going to say new. My first tilt line is this. Okay, so I'm going to pick about 8 of them. This is 3. This is 4. And as it comes on this side, I'll pick this edge. I'll pick this edge, 6. And I'll finish it up with these 2 edges. Sorry, this one, I'll reverse it, and this one also I'll reverse it. Okay, I have got 8 edges now, and I'm forcing SolidCAM swarfing to follow these edges. Okay, already it says the geometry is invalid. Let me see if I already have some geometry with me. Okay, let me pick contour 5. That's the geometry. Let me go to the tool. The tool is the same. I'm not going to do any changes now. I'm just going to hit save and calculate. Okay, let's run the simulation. And I have, again, this tool. This orientation is fine. What we have to worry is only in this corner, because that's where the whole problem was. It's doing nicely. It's following. And as you can see that in between these two, it changed its, what you could say, the tilting. But you can control it. You can have few more lines on this, and the tool will continuously keep following those lines. And as I go forward, it's again following the same lines. Now we no longer have that crazy move in which the tool almost started becoming horizontal. So we have got a very nice tool path now. What this also demonstrated was the fact that in spite of having everything automatic, you still have options to control many things in swarfing, but they're all switched off. You need to switch on only when you get into issues where you need, or when you need more control of the toolpath. As you can see, right from swarfing onwards in SolidCAM, a lot of things have been automated. Where all can you use it? Well, application-wise, the first application that I can think about is in machining of such frame parts, where generally people would machine this using 3-axis. They'll go with multiple depth of cuts, whereas it's 5-axis. You could just go single cut, eliminating all those multiple cuts and save hell a lot of time. You could also use swarfing as a finishing tool for finishing the sides of an impeller with a cross section in a straight line. You could just say one pass around the entire periphery of the impeller, and you could have your finishing done instead of giving multiple passes to it. So straight away, I have two applications where swarfing can be of great help to the user. All right. Let's now move into another new area that was developed inside SolidCAM, and that's for machining impellers. It's also called as multi-blades in certain regions of the world. So the whole technology is being called as a multi-blade machining. I have this very nice impeller. Now, if I had to ask many of my users that I have this impeller, please cut it for me in a regular SolidCAM 5-axis. Now, it's not possible, or it's impossible. It is possible. It's very much possible in our regular 5-axis machining, but the amount of time and the amount of geometries that needs to be created to cut such impeller is tremendous. It's too much. And it generally leads to a lot of turnaround times for programming such parts. Now, what we have in the new version of SolidCAM, in a new version in 2013, we have got a dedicated application for machining such impellers or multi-blade parts. Now, your impeller could have a single splitter. A splitter is a small geometry in between the two main blades. Or it could have multiple splitters. It actually doesn't matter. But as long as you're able to provide this information to SolidCAM, you are perfectly fine. So what I'm going to do now is I'm going to run the multi-blade operation. Now, if I go to the milling operation, I have got this multi-blade machining out here. This is a new function inside SolidCAM 5-axis. In the multi-blade machining, we have got 4 sub-operations. One is the roughing of the multi-blade part. The second one is blade finishing. The third one is hub finishing. And finally, the fillet finishing. It's logical. You have to do the roughing, your blade finishing, floor, and then the fillets. Let me start with roughing. Now, if I jump to the geometry, you can see that the geometry area is pretty clear. meant for people who are just starting new onto SolidCAM. They can easily pick up this. First is a strategy. We have got three strategies. First is offset from hub. A hub is basically a revolved surface. This one, this is called as a hub inside the multi-blade. Or it could be an offset from the shroud. A shroud is this small piece of surface that covers the top of your blades, be it the main blade or the splitter. Or it could be a morph between the shroud and the hub. So I'm going to use that strategy. I'm going to offset between the hub and the shroud. The next it's going to ask me is pick up the blades, splitters, and fillets. Let me check in my geometry if I've already got that. Yes. I've already selected these surfaces, so I'm going to pick from the existing geometry itself. Say OK. I want to keep a stock of about 0.2 on the blades for my final finishing and the fillets. On the hub, let me check if I have the hub surface with me. Now, the best part of the multi-blade machining is even if you have a small surface of the hub, it's more than enough. You don't have to select this entire surface as a hub. It's not needed. For example, I have the small surface out here, which is basically the hub. It's only a portion of the entire hub. It's not the full hub. But I can select that as my hub. And the same goes even with the shroud. I don't need to select on all the blades the shroud surface. I just need to pick one of the shroud surfaces. SolidCAM understands that it is a revolved surface, so internally it's going to do a surface of revolution. Okay. Let me go to the tool. Slightly different here. I'm using a taper ball nose in this case, which is pretty common when you are cutting impellers to use taper ball nose tools. And we're going to use this taper ball nose to cut this impeller. Select levels. You can see it's put on auto detect. There's no longer definition of parameters, values to be input, type of clearance areas to be selected. It's all automatic. I just need to pick this button, auto detect dimension and position. Next to the toolpath parameters. Now, how many layers do I want? That means how many depth of cuts in actual I want. Okay, I want 10. And what is the maximum number of layers in slices in terms of radial depth of cut you need? Let me put it at about 12. Okay. And I'm not going to start exactly at 0. That means I'm not going to start exactly at the edge, but I'm going to start about 1% below, and I'm going to stop exactly at 99%. I'm not going to go to 100%. This is generally done so that if there are any surface edge issues, those are taken care by this 1% moving of the area. In the tool axis control, again, you can see there's nothing. Everything is default, works fine with the most default values. In the link, also everything is automatic. See, we are not inputting anything in this case. We are using automatic wherever possible so that our inputs to SolidCAM is bare minimum. Gouge check I don't need because most of the gouge check is already inbuilt, but you could be in a position where where your tool arbor might be touching one tip of the blade, and that's where you need the gouge check. Otherwise, you really don't need to switch on the gouge check. Roughing and more, since I'm going to machine from I'm using the offset from hub to shroud, I don't need to define the stock because it's already representing, that shape is already being represented as a stock. All right, let me save this and start calculating. This will take about a minute to calculate, or even less. Okay, it's finished the calculation, and if I now switch on the toolpath, you can see what it has done. Okay, there's a small thing that we had to do and we did not, was to change this machining. Now it has done a one-way machining. We need to do a zigzag. So let me edit this toolpath. Go to the toolpath parameters, and under sorting, I'm going to make it zigzag starting from the leading edge. Now, in a multi-blade, you've got different definitions. In about a week from now, we will be having our first tutorial of multi-blade where everything is going to be explained in detail. For example, in a multi-blade, you have got a leading edge. You also have got a trailing edge. Well, let me save and calculate. Yes. Okay, it's almost done. We come out of the toolpath calculation and show you the toolpath straight away. It's much nice now. You can see how the connections are happening. Very nicely connected using the blend option. It's not jumping every time to the clearance plane to do any kind of linking, but most of the links are happening within the layer. So extremely nice and clear. If I want to run the simulation in Solid Verify, we're going to have it very soon. Let me switch off the fixture. Let me switch off the holder. Let's run quickly. I'll show you a few cuts on how this looks like. So roughly this is how our roughing would look like. And as it goes, it will further go into the depth and generate the final roughing for us. Looks pretty good. Let's move to the next option. Set rooftop so that I can have a much better background view. All right. So I'm now going to run the multi-blade operation again, and instead of roughing, I'm going to do the blade finishing, and then let's do only the main blade finishing. I'm not interested in doing the splitter because it's just to show you the capabilities. The blade splitters and fillets. Now I'm going to again pick from my existing geometry. This is my single blade, and we're going to finish this blade. Okay, let me edit this because as I see a small missing surface out here. I'm going to pick that surface also as a part of the surface. Okay. And offset from hub and shroud. So I have the hub, which is basically that one. I've already selected. And the shroud is faces 2. Okay. The tool still remains the same. I'm going to use a taper milling tool. Level, automatic. Again, there's nothing that you need to define out here. It's toolpath parameters. I'm not going to go do full. What does full mean? The full parameter means it's going to run around the entire blade profile, including this surface out here where my pointer is currently at. I'm not I'm not interested in doing that particular surface. I will say trim it by the trailing edge. So I don't want tool path on my trailing edge. So it will start here and it will end at the next trailing edge. And I want about 12 passes. My starting percentage in this case, I'm going to slowly increase it to 2% and I'll end it again at 99. Surface quality, I have the tolerance of about 10 microns. Sorting, I'm going to do one-way machining. It's always one way, and we will use a climb mechanism. In the edges, I want the edge roll to be set to automatic. In the tool axis control, like I said, there is not much that the user is allowed to change. Most of the things are default and they work very well when set at default, unless and until you want some result that you're expecting which you're not getting by the default parameters. You are allowed to change those values, but otherwise these values are, you could say, the final values. You don't have to touch them. Most of the values run very well. Link, automatic. Gouge check, we don't need because it's already inbuilt unless and until it does something very different than what it is expected. You don't need to touch the gouge check. Let's hit save and calculate. Okay, it's finished the calculation of the finishing programs, and if I run not this but the host CAD, you can see very nice toolpath, straightforward toolpath. We didn't do anything. We even included the fillets below as our cutting surface, and the software did it perfectly. There's absolutely no flaw in machining. It's a clear, smooth toolpath. Imagine machining such geometries in the regular 5-axis. It's really a big work. But with a newer system, with a new application that we have inside SolidCAM, this is much more easy and automated and gives you highly predictable results. Okay, let's exit from this. Let's also now look at how we finish the floor. So we are now going to finish the hub. And in the geometry, again, it's asking me for the blades, splitters, and fillets. You can see that it's a repetitive geometry, so I need not keep selecting it every time. I can just store it and just call it. Now, these are again my geometry that I have selected. And the hub is basically this small surface. I don't have to worry that I have such a big hub here and I'm selecting the hub somewhere else. It's not really needed. It just needs to know what is your surface of revolution of your hub. I'll leave about 0.1 millimeter of stock on the walls so that it doesn't touch the blade. Use the same tool. Go to the levels, auto detect, toolpath parameters. I'll say a maximum of 25 cuts that I want on the hub. That should be good enough. And sorting, I'm going to go zigzag starting from the trailing edge. From the small edge, I'm going to go up and I'm going to order from left to right. It should start at left, end at right. Okay, tool axis control, nothing's needed. Link, also everything's automatic. So let's again hit save and calculate. You can see how quickly we are generating the operations for a multi-blade part, which otherwise would have taken a lot of time, it would have consumed a lot of time. It would have generated a lot of fatigue to the user who was generating this program. Now if I show you the toolpath, you can see very nice, straightforward toolpath for machining the floor. Clean. If you want, you can have much more dense toolpath, but I've just shown you for the sake of demo. We've taken about 25 cuts on the floor, which generates a pretty good result. So the end result is that we're getting a much better result than we would get using our regular 5-axis because of the amount of geometries that we need to construct. Right. Now the last thing I want to show you on a multi-blade is how do we finish off these fillets, because in real cases, in practical cutting in impeller, we'll never have a constant fillet at the bottom. The fillet will always be large and it will be variable, and it will be almost impossible to take the entire fillet and cut it in the finishing operation itself of the blade. So the finish of the fillet must be handled separately. And this is what we're going to do now. I'm going to add milling operation for multi-blade. I'll use the fillet finishing, and the geometry, again, I'm going to select the blades only. So that's, since I want to just do the fillet of the main blade, so it's faces 3. The hub is face 1. That's not changed. The tool I'm going to use is a taper mill again. Levels, automatic, toolpath parameters. Now I have got another parameter window here, wherein first I need to specify if I'm going to machine the entire contour or if I'm going to trim at the trailing edge. I'm going to trim at the trailing edge, and on the blade sides aside I want about 5 cuts, and on the hub side I want just 4 cuts, and the side step here is about 0.5 millimeter. All right, let me save. Everything else is a constant. There's no change in the parameters, and they are all default. Works fine. Let's hit save and calculate. Okay, that's done. Let's check how the toolpath looks like. Very nice. You can see how the toolpath is merging itself from the blade onto the floor, and it's flowing all the way around your blade, right on the floor, machining the blade and finishing the fillet. So we have about 4 passes coming from the hub side and 5 passes coming from the blade side, and merging and machining the fillet very nicely. Now this is another key feature in multi-blade machining on how you can finish the fillets. Right, so we have seen swerving and we have seen this new application for multi-blade machining. Let's move to another area, and that's trimming of vacuum form parts. So let me open a part. Okay. So we have got this part out here whose edges need to be trimmed out because it's a vacuum form part, and I want to trim it exactly to this edge, because in vacuum forming you really don't end up getting this edge. So we need to form that. So what I'm going to do now is I'm going to add a milling operation, contour 5-axis. Again, this is a new function inside SolidCAM 2013, 5-axis. Pick that. And the geometry, I have got my drive curve. I think I already have defined it, or if not, I can always define it using the selection process. So it appears that I really don't have that contour, so let me define a new drive curve. My new drive curve is this one, 2, 3, 4. I've got this 5, 6, 7, 8, 9, 10. I'm selecting the outer segments, and the outer segments will then guide the tool. Now the best thing about contour 5-axis is it really doesn't need your surfaces. It doesn't need surfaces because tilting mechanism is completely different. So you can see that you don't have any surface selection inside contour 5-axis. You just select the drive curve, and then you have got the orientation lines. Now orientation lines are nothing but your tool tilt lines, which are going to control the axis of your tool. So I'm going to say new. I'll say new, and I'm going to select these lines out here. So I've got 1, 2, 3, 4, 5, 6, reverse this, okay, 7, and the last one, small one, that's 8. So these curves are now going to define the tilting of my tool. All right, let me select tool. It's a 6mm end mill that I'm using. Levels, again, plane height is now defined at 50. Now this is slightly different than what you saw in multi-blade and swarfing. Here I need to put some parameters. Tool path parameters, tolerance is 10 microns. Tool axis control, again, same like our regular 5-axis. We're using the side tilt definition as a default, which is orthogonal to the cut at each position. And I'm not going to define anything else and just hit save and calculate. Oops. What was the problem? Okay, let me change the snap distance. 5. Strange. Do I have the okay, let's redefine the inner contour. Now I know why it's creating this. That's because when I have the contour, it's expecting a tilt line at every place where the contour is broken up. So I need to switch on another sketch also. We need to define the sketch also here. So I've got a mix of all sketches, so let me redefine the contours. Only the tilt lines has to be redefined now. So I've got 1, then I've got 2. Wherever the surface or the edge is broken, I have to define a tilt line. Okay. Right. This one. Okay, sorry. This one, and then I have this one. What I have here is this one out here. Okay. And we have got another tilt line. So wherever the tilt line is changing, I need to define. Now I'm going to select the upper one because I want the orientation to change here. So that's the reason I've got the tilt line. Reverse. Okay. That, even this one. Another tilt line. So I need to keep defining the tilt lines on how I want the orientation. This is very useful, especially if you're trying to control the tool axis tilting at certain positions where you want it to change in a certain way. This tilt lines become very useful for us. Okay, that's accepted. Let's get back to the original dimension of 0.1. Let's save and calculate. Right, that's done. So if I now run the simulation, we have another problem, and that problem is because of the tilt here. It's be set to 90. Let's calculate. Done. Let's run the simulation. Right, that's how my tool is coming up. And you can look at every point it's cutting. It will always follow the tilt line. No matter how the tilt line is, it will always follow the tilt line at that particular point where it is supposed to wait. Right. Now I can see that as it comes out here, there are 2 positions for it. One here and the other one here. Depending on what was the tilt line defined, it's going to orient itself. Now, the bottom line was defined, so it's now going to orient it according to the bottom line. As it goes further up, and as it comes and rolls on this particular edge out here, this particular line that we have, it's tilted below Now you can see how it influences the tilt of this particular point. You can see what is happening out here. The tool is now trying to maintain itself as close to this orientation of that tilt line as possible. You can see it's almost the same orientation. Goes up again, and now you can see that there's going to be a major change in orientation because I've picked these two big lines which have got positive orientation. There it is. It's moved up. It's moved up, and it's trying to align itself to those two orientation lines. And as it finishes, it comes down again to try and orient to the next two lines. So depending on how your orientation lines are, it's going to orient itself accordingly. And that too without any surface. So if you don't have a surface, you don't need to have a surface. All you need is to have just the contour curve and the tilt lines that are going to actually guide this tool to cut the part. All right, so this is a very useful application when you want to do cutting of the vacuum form parts. It's a big market. I know that very well. It's a vacuum form parts are big markets. Even in aerospace industry, where there are a lot of aluminum sheet metal parts used, this technique of contouring is used in 5-axis to trim out the profile at the bottom, because these parts actually go and fit on some other parts, and the bottom profile is very, very important. It needs to be pretty much accurate so that it goes and fits itself very nicely on the panels. Right, now I'll come to the last part. I have picked up this part because it's pretty interesting. Of course, there's nothing new in this, but I've picked up this part because it sounds very interesting to me. It's basically an extruder screw that I have, that you're going to see on your screen now. It's an extruder screw, and we would like to cut this in 4-axis. Now, the surface looks very nice, but they're all broken up. And if you are trying to use a regular morph between two curves, or morph or parallel to curve, and selecting this as a drive surface and trying to do some operations, you're going to be in for some major issues, because the tool will try and always orient itself with respect to these surfaces, and these surfaces are changing at every point. So it's going to be very difficult for the system to accept these surfaces and generate a precise tool path. So how do we cut this parts? Simple. What I have done is I have generated a simple oval, an oval geometry out here. It doesn't matter what is the dimension. A simple oval geometry which looks similar to this. And what I've done is I'll add 5-axis, 4-axis rather, and we're going to use the morph between two boundary curves. The drive surface is, if I have to pick up, not that, yes, this is my drive surface. My drive surface is this oval-shaped part, oval-shaped surface. Start and end at the exact surface edge. The start curve is the contour, and my end curve is contour 1, the other side. So what I'm trying to do is I'm going to cut the internal surface. I'm going to use a 10mm ball nose. Toolpath parameters, I'm going to give 2mm as my side step, and I'm going to do a spiral, a nice spiral on the geometry. But what I'm going to do is, instead of actually cutting this surface, I'm going to use the gouge check. I'm going to trick SolidCAM here, and I'm going to use the gouge check to check for gouges on the tooltip, tool shaft, arbor, and holder using a check surface. Now, which are the check surfaces? My check surfaces are these surfaces. So I'm going to trick SolidCAM into making a gouge on purpose, and then realizing that it has gouged it, it's going to pull the tool and push the entire tool path onto this surface, which is a very nice capability inside SolidCAM. Let me hit save and calculate. it's done the calculation. Let's see how the toolpath looks like. Nice. You can see how the toolpath is. If I run the simulation, of course I have to change some things in the retract type. I've just kept it at Z, so that's why you're seeing those two lines. But it's doing a very neat job. It's following the bottom surface but cutting the upper surface. So it doesn't matter what kind of a surface that we have, but it's doing a much neat job when it comes to projecting this toolpath back onto the upper surface. So using this, you can actually cut any kind of rotary parts where the surfaces are not uniform. They don't have a specific direction, shape, or the isocurves are completely disoriented. You don't have to worry. All you need to do is to create a simple shape below, cut that shape, and project the toolpath back onto these surfaces. Right. So we have come to end of our part 1 of this seminar, of this webinar. And if there are any questions, you can ask me the questions. Else, we'll be meeting again next week, same time. Sydney?
Okay, Amod, thank you very much. It was an extremely interesting webinar. There are no questions at this point, but this webinar will be available to them later on. אני רוצה להודות לכולם שהשתתפו בוובינר. שבוע הבא אנחנו נמשיך עם חלק 2 של הוובינר הזו, ומקווה לראות את כולכם שמה, וזה נושא באמת מאוד מעניין. אז תודה רבה לכולכם, ושיהיה לכם המשך יום טוב. Thank you very much, Amod.
Thank you.